this actually needs to be link in this case. So here's a weird thing. I'm going to go back and I'm going to do this where we add the prediction from the model coefficients to our simulated data, right? So new data 2 is our simulated data. So we're adding the prediction to the simulated data as a new variable. But this time I'm going to use type equals link because it's going to be easier for me to construct the confidence intervals later on if I do it all together all at once with another function. Okay, so we're binding the columns of the simulated data and the prediction where type equals link, and I want standard errors as well. And the data, the new data is actually an argument in predict, and it's going to be called new data 2. And this is going to become what's called new data 3. And then we can look at it. And we have fit and SE fit, which are the ones that will matter. Those are in the logit, but we are going to convert them back to predicted probabilities ourselves rather than through the argument. We're going to do that through the p-logis, which translates a fitted value into a predicted value. Translates, in this case, a logit prediction to a predicted probability prediction. So look at the new data fit is, again, should be 400 values, and those 400 values are in units of logit. Okay? The p-logis translates that into probabilities. So it does the exp x beta over 1 plus exp x beta for us. And you see the exact same variable wrapped around the p-logis function gives us all these predicted probabilities. So everybody gets their predicted probabilities here. So this, the reason why I'm doing this and not just doing the type equals response this time is so that I can construct the confidence intervals using the fit plus and minus 1.96 times the standard error, the fitted standard error, which gives us all the bits that we need. So this is all in logit, and then we wrap the p-logis around it. And so we're going to get the lower end of the confidence interval on this first line. We're going to get the actual fitted line here in the second line, and then the upper end of the predicted probabilities here. So with new data 3, I'm adding 3 new variables, pred low, pred, and pred high, I call them. And they're going to give us, glimpse, new data 4. So you can see now we have our simulated data up here. We have our original fit and SE fit that were in the logit. And then I used p-logis. I added 3 new variables that are the lower end prediction. So the predicted value minus 1.96 times the fitted standard error. And then the actual prediction. And then the upper end of the 95% confidence interval with the pred high. And so now we have everything that we need to plot, and we can go ahead and make our plot. You remember that pretty plot that we showed earlier on? This is the code, all the code that it takes to do it. If you're not familiar with ggplot2 and tidyverse, I'm going to explain this briefly. So you always start with the data. And with the piping, this thing is awesome. And if you don't know tidyverse, you eventually want to know it for piping, if for nothing else. Piping allows you, sometimes you need to do a function and then a function to the function, and then you need to do command after command after command all at the same time. And you do it inside out, and each command has its own set of parentheses. So you have like a turducken situation, Thanksgiving style, where you've got one function sitting inside another function, and each of them have their own set of parentheses, and by the end, you're in a web of parentheses, and there's 4, 5, 6 layers of parentheses around an individual thing. What the pipe does is it lets you unravel all that and you do it sequentially instead, and it's super helpful for seeing code and explaining code. So here what I'm saying is I'm starting with the data, and then we always start with ggplot here. ggplot works in the quote-unquote grammar of graphics, and ggplot requires that you set aesthetics, and what aesthetics are in this case are what components of your visualization are going to be set to a physical visual element of the plot. And in this case, we have a few aesthetics, but I'm just going to start by setting x and y. X is going to be the GRE score. Y is going to be our main predicted probability. And then after this, when you start ggplot, then you do pluses until it's over with. Then there are a lot of different geoms. Geom is like what's the shape that's going to be plotted now on this layer of the plot. Geom line for a line plot, geom point for scatter plots, geom box plot for box plot, geom histogram, geom density 2D for two-dimensional densities, etc., etc., etc. In this case, we want the ribbon, which is going to do a high and a low, and then it's going to color everything in between, which is exactly what we want. We already have the Y aesthetic set, so we want the low and the high in the ribbon, and then we want to set one more aesthetic. So remember, in an aesthetic, everything that comes after that aesthetic is a variable. So X in the plot is going to be GRE. Y in the plot is going to be the pred value. The Y min for the ribbon is going to be from pred low. The Y max is going to be from pred high. And then fill means what are we going to use to color the ribbon? And by setting it to rank, remember rank is a factored variable, so it's got different layers, different categories. 1, 2, 3, 4. It's going to make 4 different ribbons of 4 different colors based on the rank of the school. This is where it's going to break it apart and give us 4 plots for the price of 1, basically. And then alpha is outside the aesthetic. This is no longer an aesthetic. Alpha is for transparency, so you can make colors. It's not actually transparent, but what it does is it does a little bit of math and figures out the color in between the two that's going to make it look transparent. And by the way, there are 17 million roughly colors in a computer that you can get to through hex codes, and which is why I use hex codes for pretty much all my colors. For red, blue, green, but you can do it that way too. And then geom line, this goes with the aesthetics up here, X and Y for GRE and pred. So this is the main line. And I add color for rank here because lines don't take. Fill is for something with area that fills it in with color. A line doesn't have area, so you can't fill it in, so you can only color it. So the aesthetic is color equals rank here. And I've shrunk the size just a little bit. And then labs is, as you would expect, labels. So I've labeled X and Y. I've given it a title and a subtitle. And then setting a color and a fill lets you change. There's going to be an automatic legend on the rank variable from the aesthetics that were set up here with fill and color. It allows you to set that. And I wanted them to match, that way there's only one legend, because I don't want there to be a different legend for color and fill, because as you'll see, they're going to be the same. And then I set unique colors. I didn't like the default, because the default was what's called a qualitative palette, meaning 4 colors that are completely different and there's no real rhyme or reason to the order. That's like what you would do if you were making a map of the world and you just wanted different countries to be randomly different colors, like you would see like in a globe that you would play with as a kid or something. I want there to actually be an ordinal shift in the colors because the rank variable is actually an ordinal variable. 1 is lowest, 4 is highest, and I want the gradations in there to be roughly equivalent. So I'm going to have it transition from a green to a blue, or a blue to a green, and I've chosen these hex codes, and they have to match because this scale color matches the line that has the color aesthetic. So this one is setting color for that line, and then this scale fill is setting the fill for the ribbons. Okay, so that's why there are 2 of these, and that's why there are 2 labels here. They're exactly the same, but because the aesthetics were different, I had to set different lines of these things. And then finally, I reversed the legends on both because the default is going to have the lowest. So rank 1 was going to be the highest visually, and I would rather it be the lowest visually, so I'm reversing the order of the legend. And then this just cleans up some pretty details. And so we're going to do it. And the resulting plot looks something like this. You get these cool ribbons that match the colors of the lines. These are the geom lines. These are the ribbons. And we can see that at really low GRE scores, it's highly unlikely that you're going to get admitted to graduate school. Even if you're at the lowest ranked school, you're you're applying to a school that is considered to be of lowest rank, which is the blue. As you get to a perfect, let's say this was the math section and it got to 800 and you got a perfect on the score. Your predicted probability for getting in is only at about 0.63 or so for even the lowest rank school. The highest ranked school, your probability is only at about, it looks like, I don't know, a little over 0.25. Keep in mind, typical schools that are ranked that high, the rejection rates are anywhere from 7 or 8% to get accepted, so 93% rejection rate to something in the 80s at least. So this is actually above average in this case. But remember, we also pinned this to the GPA being at its mean. So you have a very average GPA, but you really kick butt on the GRE score. And then you apply to one of these 4 types of schools, and this is the profile of what the predicted probability would look like. But this is a very clean, understandable, predicted probability makes a heck of a lot more sense than log odds, odds ratios, etc., etc. Makes a lot more sense to say, what's the predicted probability that you would actually get admitted to school? I think everybody can get around that, and they can get behind that, and it's sensible. You can see it, you can visualize it, you see the movement. Elite and upper middle are very similar in their profile, it seems. It's not until you get to the lower middle rank or the lowest of the rank that there's actually some shift. Okay, I hope this example for how to create a logit and your own predicted probability plot made sense. I hope it was fun, and you can make some really cool plots. You're going to get a chance to do this in assignment 4, so this helper script will also be available to you so that you can work on your own. All right, take care.